Eddy current, sir. LC oscillation and this thing. No. So those are online. Are you able to hear me?
Yes, sir.
Okay. Okay. We'll discuss LC oscillations. Right. Shall we get started? So what do you think happens in LC oscillations? I think I gave you the outline already, right? What happens? Of all the circuits that we saw till now, we had RC, RL, and RLC. We had, that's it, no? RC, RL, and RLC, right? We didn't have LC at all. So as I told you, when you use an inductor and a capacitor, right? When you use an inductor and capacitor, you don't connect any external power source, right? So at that point, the charged capacitor itself will act like a battery, right? So when you have a fully charged capacitor, first thing that we need to recollect is okay. When you have a fully charged capacitor, the first thing that you need to notice, it has energy stored in the form of electric field. It has the electrostatic energy stored in it. What will happen to that electrostatic potential energy? So what is the value of electrostatic potential energy that is stored in the first place? UV is equal to half CV square. We know this. What will happen to this energy? It will start getting discharged, right? When the capacitor starts to get discharged, it will start creating an alternating flux across the ends of inductor. So when there is a change in flux taking place at the ends, taking place through an inductor, what will get generated? There is something called as back EMF that will get generated, right? So when this back EMF is there, can I say energy which was electrostatic is getting converted to magnetic? Because what is the form of energy an inductor will store? Magnetic energy. And what is the value of the energy? It is half LA square. You remember this value? We derived it in the previous chapter. So electrostatic energy is getting converted to magnetic. Now what will happen is electrostatic energy will completely become zero and the magnetic energy will reach to the full value. After that, the magnetic energy that is stored will start charging the capacitor. Means if you see the process, initially it will be something like this. The capacitor will be fully charged and the full energy stored in the form of electrostatic potential value, which is getting converted to a partial magnetic field. It means this is decreasing and this is increasing. You're able to see, right? After this, what is happening? It will reach 100% value. Then this becomes completely zero. After this, magnetic energy will start charging the capacitor. Now see, the direction in which it got discharged is exactly the direction opposite to the one in which it is getting charged. Is that right? Again, energy will be partially magnetic and partially electrostatic. After that, full magnetic energy is lost and the energy gets completely converted to electrostatic. Like this, the process keeps on continuing in such a way that this will generate a desired frequency of desired wave of a particular frequency. Generate desired wave of required frequency. Is it clear? So this is what happens. You can just make a note of this diagram, and whatever I told you, write it as a block diagram. Okay. Why am I stuck like this? Clearer? Done. Right. Now I have to tell you something important. You're copying whole diagram. Huh? Done. So here I told you it generates a wave of particular frequency, right? Now, first of all, we need to understand why we need this kind of a circuit. So if you see, we call it as LC oscillations. Basically, it is called as an oscillator. So what is an oscillator? This L and C put together is called as an oscillator because in communication, right? So when you talk about the communication, that is in the basic broadcasting services, that is you have this FM, right? What is FM? What is the full form of FM? FM, Nana. It's called frequency modulation. So the one which you're hearing is actually called as frequency modulation. So as the name suggests, frequencies have to get modulated. It is not modification. It is modulation. Okay, there is a difference. Modification means for the existing frequency, you're trying to change the frequency. Whereas in modulation, what you will do is, there is something called as message signal. For example, let's say there is a radio station. I have a mic here, okay, and I have all the controls. I'm speaking, right? I'm speaking at this place. What is the purpose of FM? Let's say there is some person who's traveling in some other part of the country, okay, in Tamil Nadu at least. Okay, they should be able to hear to my channel, right? Whatever I'm speaking here, how is the person on the other end able to hear it? How is the signal even get transmitted? Right? How do you best one? Radio jockeys have no other job, but frequency they don't even know the meaning of it. Okay, they work there, that's it. There is nothing of that sort. See, generally, no human being will modify themselves according to system. I talk like this, but my voice will get transmitted. How is it happening is because my voice is called as message signal, but my signal will be weak. When I say weak, no, it is of lower frequency. Lower frequency, it is not that high. Generally, frequency, when the frequency is high, right, it can get transmitted to longer distances. That is why AC has an advantage of DC. You can ask me, why can't we use the slide with the help of a DC? Why can't we have a whole electrical station where only DC is there and they supply DC to us so that all these lights are glowing with the same intensity? And the DC value should be RMS value of whatever AC we are getting. They could have used it, no. But why are they not using it? Because it is difficult to transmit. That is why we go for that. AC's advantage because we have frequency. So in a similar way, the message has to be transmitted to a longer distance. My frequency has to be high. But unfortunately, as a human being, we can't generate it. We need some machines which need to get merged with us. So there will be something called as message signal, which will get clubbed with something called as carrier signal. Name is telling you, see, carrier signal now, it is the one which carries the message to a longer distance. Okay, so these carrier signals are basically very high frequency signals. When I say very high frequency, you are able to understand what does it mean? It will be this close. I just want to show it out of my own interest. Now on the card number. So you're able to see this, no? There is actually a sound recording software. You're able to see the frequencies there, right? So generally, when I put it like this, you're able to see the distance between them. The height. That height is what we call it as amplitude. Apart from that, the way I speak is going to record my voice with a particular frequency, in the sense how fast my voice is vibrating, right? So based on this, what will happen is when I bring it like this, are you able to see? Actually, it is a click done in the software. So when you talk about a high frequency signal, it looks something like this. Means they'll be very close to each other. Whereas when you talk about a low frequency signal, the distance between each message will be slightly longer. But don't get confused. This signal is of the same frequency. We are only just doing a tweak in the software. But in reality, when you have to say something is a high frequency, the waves are supposed to be this close to each other. So if suppose you have this kind of a signal, which is called as a carrier signal, and suppose you have this kind of a signal, which is called as a message signal, these two signals will get merged together and it will be transmitted to a longer distance. And this process is what we call it as modulation. But at the receiving end, what should happen is you should not have this carrier signal because it's not a part of the message which I spoke. It is something which is added. So at the other end, what they will do is they'll remove the carrier signal and they will process only the message signal. You're able to understand? That process is called as demodulation. So modulation and demodulation. Yeah, tell me.
Sir, which part is
Which part is?
Sir, can you, sir,
Are you able to see my screen?
Sir, which
first?
part is carrier signal and which part is the message?
Okay, if you're able to see the screen on the blue color lo on the
yes.
You're able to. Okay, so when I put something like this, are you able to see the signal how it is? They have some distance. Yes. No, see, for example, I'm moving my cursor. They have some distance. No?
Yes, sir.
Okay, this is how a message signal will look like.
Okay, sir.
That is my voice. If a carrier signal will look something like this. So it looks something like
okay,
this. These two signals, when they are merged together, we call it as modulation. And on the receiving end, what will happen? The carrier signal is removed, which we call it as demodulation. In your house, you use this device for internet. What is the device we use? Router, correct? Actually, it is actually modulating and demodulating. Sometimes you call it as a modem also. Have you heard of this word modem? Modem abdina, it is modulation and demodulation put together. That is the job of the device. Purida. So you're able to understand why we are studying all these things. LC oscillation, the main application of it is, if I'm not wrong, it is a part of your activity also. You do activities, right, apart from practicals. One of the activities is an oscillator itself. Means they'll ask you to design it. Most of the time you go to a shop and buy it, that's a different story. The application is, it's an oscillator. So oscillator, why do we use an oscillator? To generate high frequency signals. And why do we need high frequency signals? In the process of communication, to mix it with the message signal and transmit it to longer distances. Question, how will I know what is the value of the frequency I need to generate? Carrier frequency, carrier wave, you are saying it is high frequency, but what is that number of high frequency I need to generate? That will be decided by the value of the inductance and capacitance that you use in the LC oscillator. Purida. Okay, I'll explain that part. Shall we proceed? So the frequency of the carrier signal that you need is given by the formula 1 by 2 pi root LC. Don't you feel you have seen this somewhere? Just 2 classes before we have seen this. Last Tuesday we saw this. Where did we see? For resonance frequency. That is defined for the sharpness of an LCR circuit. Value is the same. Okay. So when I say sharpness of resonance frequency, where do we use the concept of series RLC circuit? That's application I told you already. That is also for communication only. But in some circuit where you want the sharp frequency to come out, what circuits are they? You have something like this. You call them as tuner circuits. So you use them in tuners, whereas LC is used in generating the high frequency signal. They are called oscillators. Purida. So the value of frequency that we need to generate depends on two parameters. What are they? Inductor and the value of the inductance and the capacitance that you're going to use. Am I clear, guys? So we don't need the derivation of this formula at all. Actually, you will get a second degree differential equation which you need to solve, which is not a part of your syllabus. Don't worry about it. Perfect. Okay, the value. Accept it. Guys, is it making sense? Or like is it too much for you to receive? I'm just trying to attempt. Purida, I thought it would be interesting and I'm explaining. If you don't want, I'll stop it. Purida. So it is used to mix the except another. It will only generate the carrier wave. Message signal, your voice put over signal mix who will generate and give me that signal? That's the oscillator. Oscillator will generate and give me. There will be a separate modulator to mix these two. That will be separate electronic device. This is electronics section. Right? So with this, officially we are done with AC. The topic that is pending is eddy currents. So eddy currents will have a look at it. Shall we? Well, that also I need to show you a video. Just give me a minute. Okay. There's something interesting. I feel you will like it. Let's see. Ambar Tungram. Hey.
The chief scientist in the imagination station.
Okay, I'll just give you a. Tell me. Are you able to see?
No, sir.
Just a minute. Sorry, I didn't share my screen. Okay, so I'll just give you an introduction of what it is. Okay, so eddy currents are a part of electromagnetic induction. So what is electromagnetic induction? If there is a change in magnetic flux taking place through any closed circuit, then there is an EMF induced. So EMF induced will generally do what? Will generate current. That is why this topic alone we have it as eddy current. It is not eddy EMF or something. Correct. Other topics you talk about EMF. What is the value of EMF getting generated? So on the point first mind learn. Secondly, you will have magnetic field existing into which you will try to pass a lesser magnetic substance for you to observe this effect. Lesser magnetic, now what can you do is mostly you will pass only paramagnetic substances. Okay. So in the presence of external magnetic field, if paramagnetic substances are passed in a certain way, then these currents can get generated. Okay. So now we can ask a question, will ferromagnetic not show this effect? I'm not saying no, it will show. But the problem is ferromagnetic substances, rather than showing this effect, they are more attracted towards magnets. If you try to connect the dots and see, right, in transformer, what was the core which we used? I told you already, people also answered the previous one. We use a soft iron core. Iron is a ferromagnetic substance, correct? So when I talk about a ferromagnetic substance, how can I talk about eddy current loss if I say that it doesn't happen? Transformer, what is one of the types of losses? Eddy current loss. So how do you eliminate it? By using a laminated iron core, correct? So ferromagnetic laguda, you will have it. But if you want the effect to be observed better, then you need a lesser magnetic substance. That is why we do the activity with the paramagnetic substance. Okay. Now see what is going to happen. Are you able to see? I don't know how to put the sound there. Next time I'll research. The sound I don't know how to bring it. They talk for so much time. Okay. You have a. So he is having a copper plate in his hand, and he was trying to show that magnet does not stick to copper. So other thing is he'll have a steel plate. So you're able to understand this is a magnet basically. That magnet is swung on top of a rod, a metal rod, or a sheet, I will call it. And the metal sheet, if I'm not wrong, partly it is copper and partially it is iron, a ferromagnetic substance. So tell me one thing, what is the science involved behind its oscillation? Initially, he put it at a certain place and it started oscillating. Basic essence, the gravitational. Who's moving it? When you take it here, mg sin theta is what is pushing and it starts oscillating. and an unbalanced force is putting it into oscillation. And that's the logic. Now, if you take the magnet closer to the steel plate, see what is going to happen.
Interesting physics of that happens when a strong magnet moves close to a conductor. Remember, this is not magnetic, right? So when you pull it back, right, and then 6 inches on the foot,
What do you think will happen? Stop or oscillate? Slow down, stop, oscillate. What will happen? When I don't know. Shall we see?
maybe too broad.
It stopped because it went and hit that plate. புரியுதா? அவன் cheat பண்ணாம.
See that same thing again. How's the elevator?
Now see, it is slightly away.
Okay, so
It stops.
near the top of the plate, it just comes to a near dead halt.
Previously, it was swinging. Now, yes, it was under oscillation. Now, it came to an instant rest. How did this even happen? Magnetic force not about taking it. It should break the thread and come out and go and stick to that. No, that's not happening. They're trying to separate it. Okay. So external force is acting. If you say external force, what is that external force? What is the name you will give to the external force? Tension is acting in the upward direction. Okay. It should stop, but that depends on the strength of the magnet also. So you mean to say magnetic field is constantly changing? So when it was outside, right, was there any flux that was associated with the steel plate? Was there any flux associated with it? No, right? When it started entering the plate, there is a change in magnetic flux taking place, and its value kept on changing. And due to the change, what will happen according to Faraday's law? EMF will get induced. That EMF will generate currents. So I tell you what eddy means also. Okay, this is a very simple thing. Okay, you're able to see that it stops. Okay, let's accept it. We'll think of the theory later.
It's creating circular currents in the copper plate. Those circular currents create.
So he's actually giving you the explanation. You will not be able to hear.
Sounds like a lot, but right. The effect is it comes to a dead halt. It's not really, it just finds one.
Okay, this is not the interesting part. Look at this. That plate is there, no? So you're able to see two magnets there, no, on the top. So the plate is there. Now he's holding it. So weight is balanced by the upward force exerted by his thumb. It's under balanced condition. And the instant he releases it, what is your expectation? Will it travel along the track or will it stop? Will it travel along the track or will it stop? Stop. Summa sollunna. Think the logic use பண்ற. Magnet எங்க இருக்கு? Magnet is at the top. Another magnet is not moved. Those two magnets are fixed on the track. I'm not able to see any other magnet. Okay, but you see the way flux is getting associated. அதுக்கு என்னன்னா உனக்கு வேணா previous frame நான் காட்டுறேன் பாத்துக்கோ. You can check the size. You can ask me, sir, what is the size of the magnet? நீ உண்மையிலேயே R&D பண்றவனா இருந்தா அந்த கேள்வி கேட்டிருப்ப. பாத்துக்கோ, size of the magnet தான் நான் காட்டிட்டேன். Okay, where is he holding the plate from? Is he holding from the end of the magnet or in between the magnet? நீங்க யோசிச்சுக்கோங்க. I don't know. Okay, my job is only to confuse you. I will confuse you with hundreds of questions. And he is stable. Okay, near where is he? Is it related? Is it associated? Is there any flux link? So what should happen? It should travel down under the influence of gravity. So to show the seriousness of the impact, it creates. See what it happens.
If we make a mistake. No, it's easy.
If there is a mistake, see what it happens.
Secure it. Okay. We don't want to have that happen. Okay. So don't put your fingers down.
No, the magnets are there. No.
It's called eddy currents. So they got force
What that explain? So one magnet is moved here. So what happened? Initially, he placed the carrot there, and the carrot got cut into two pieces. Imagine that was his finger. Would have been the worst accident ever possible, right? Video would have not come out. Okay, now see, he has moved the magnet and he is risking to keep his fingers there. See what he happens. See. Did you see what happened? Why did that happen? Partially, some magnetic flux was changing within the plate, due to which there were inner currents, eddy currents that got generated and they stopped. And eddy currents, they are stopping because of the principle of Lenz's law. What did Lenz's law state? It will always oppose the cause. This is the meaning of opposing the cause. Okay, now what he will do is we'll bring the other magnet also down. See what he has. Yes, sir. So what he did is he released. So previously it was released from below the first magnet, below the right side magnet. Now it is released from the top of the first magnet because there was already eddy current generated there. Here it got nullified. Now if it is moved slightly down, see what will happen. So where do you think it will get slowed down? Near the first one, and second it will be fast.
So, you know, you'd say, why do you ever
Breathe
need
up.
weird physics phenomena?
Now here what do you think will happen?
When it comes in at the end, it's this effect. Little copper plates drop down between strong magnets, guide the moisture to a stop. So yeah. Oh, that's cool.
Right? So the effect should happen at the same time. It should not happen with a small time difference also, because the effect will get nullified. Breathe up. So this is what happens. So the pendulum came and stopped, right? You call that as a breaking pendulum. So can you tell me where is it used? Where is this phenomenon used? Or where can you use it? But all I teach you a concept today, something like this. Science expo, yeah. Where will you use it? I'll give you a hit. Theme parks. Theme park.
In roller coaster.
When you talk about roller coaster, generally what happens, you will have it in different directions, right? When it goes in this way due to gravity, it will start traveling faster. If the same speed is maintained and if you go with the same speed in the upward direction, right? With the jerk, your body parts will get damaged for sure. No doubt in that. So it has to get slowed down. Okay, because our body also has some threshold beyond which when your bones also can't sustain. So they have to calculate all those things and ensure that it gets slowed down to a certain extent and then goes in the upward direction. And that process is called as damping. Means the reduction of speed, or you call it as a braking system. Right? There, this concept can be used. Does it make sense? Right? So it's actually an interesting concept. So this is all about eddy currents. Okay, this one, this is a very, very, very theoretical one. We'll see. So you have, so this is the textbook one actually. You'll find it in your textbook in one page.
Or a piece of steel, it would stick, and I
So he's using aluminum. This aluminum. Audible.
wouldn't be strong enough to pull it. So the point has also.
So there are three kinds of plates that are available. One is a fully closed plate, like the one with which you make the dosa. I don't know. Then the second one is with some slits in it. Slit now opening, which is closed at both the ends. So this is the one. And the third one is a comb-like structure, where it is open at one end and the other end is closed. Okay. Now, what will happen when all these three plates are passed through the magnetic field? Let's see what will happen.
Have slot action freely swing.
So it is swinging, right?
Okay, so now let's see what happens when I try to swing this one through the magnetic field.
Varun Shara. Captions, how do I remove? So did you see what I've said? It stopped.
Okay, notice how it breaks and stops. Now, if I did the one with the flux,
So when you try to pass with this kind of a structure, what do you think will happen? Will it stop or not? If you slow down, you have to say something. No, slow down is retarding. Retarding, there should be a point where it comes to rest. Does it come? Does it come? So it will go in the second round, it will come to rest. Is that what you think?
we see it also breaks and stops. Not
So what was the difference between the previous one and this one? So it was instantaneous here. It's taking some time to come to that halt position. What do you think about the complex
quite
structure?
as quickly. And finally, the ones with the grooves, so that
So what will happen here? It comes back and stops, no?
there's no connection on the bottom,
Doesn't stop,
swings freely.
doesn't stop.
Okay,
So it's getting damped only because of the air resistance, not because of the magnetism.
what's happening is that as
You can use water principle. I'm only talking about the principle. I didn't see the design of how it works.
so that set
So you're able to understand this one came to instantaneous rest. The second one came to rest, but it got slightly slowed down and then came to rest. Third one didn't come to rest at all. Okay.
up a resulting current increase. Where current, you don't starting magnet verify
Okay.
any current.
So the theory is this is a magnetic field. You use a magnetic substance like this, right? North pole, south pole. The field is in this direction. So that is why it is into the plane. So into the plane, if that aluminum rod was passing, what would happen?
Start to occur and the result in that of course X is circle like this.
So see, that sheet is there, no? When that sheet is entering, what is happening to the flux associated with it? It starts increasing. Then what does Lenz's law tell us? When there is a change in flux taking place, there is an EMF induced, which will exactly oppose the cause. So how is back EMF? Inductor we use the word back EMF. Okay. Here we call it as an EMF will get induced, which will oppose the cause. The name of it is not back EMF. So yeah. So when it is entering, right now, what is going to happen? The change in flux will create an EMF due to which the current will get generated in which direction? So think, no, is the flux increasing or decreasing? Flux is increasing. If there is an increase in flux taking place, will the same pole get generated or opposite pole get generated? Increase in flux will generate same, increase in flux same, decrease in flux opposite. So increase in flux will create the same pole. So if you look at the previous scenario, right, who's north pole and who's south pole? You have a paper, if there is an into mark pole. So who's south pole and who's north pole? Paper is the south pole because it is decreasing and we are the north pole. So flux is increasing the same pole as what VR will get generated. What are the north pole? So if it is north pole, then what should be the direction of current in it? Anti-clockwise. That's what happens.
Slide in like this. See, we know we generate in twice. So that's going to generate.
So you're able to see those anti-clockwise currents.
Field that's coming.
Now you already know the logic because of Lenz's law. We are not stressing on that. So these currents which are actually getting it generated in circular loops are what are called as eddy currents. Basically, eddy currents are nothing but circular currents. The whirlpools are that also they call it as eddy only. Those are also called as eddy currents. Something which takes a circular shape of current, we call it as eddy current or Foucault current. Foucault is the name of the scientist. That name is not used often. So you either call it as an eddy current or a circular current. Sharia. So this is how it will get generated, and due to this eddy currents only you could see that the braking system got applicable, which happened to the copper plate thing when it was falling. No, these are the kinds of current which got generated due to which there was a braking thing happening. But since current is getting generated, if it is passed through a metal for a longer duration, then obviously heat will get generated, and that loss is what we call it as eddy current loss, which takes place in the transformer. So to avoid this only, what we do is we generally use a laminated iron core. Breathe. Are you able to connect all the dots? Does it make sense? So the whole
Yes,
of
so-
these chapters have application. Yeah, tell me, Nitish.
Sir, so the laminated iron, it won't, the
Core?
magnet field won't penetrate into it.
No, it will penetrate, but the loss can be reduced. You cannot 100% avoid it. That is why the method is prevention. It's only a
Thank you.
prevention. You cannot avoid it completely. It will be there. So yeah,
Yes, sir.
what happens guys? Right? So this is all about what did we discuss? LC oscillator. We saw the application of it to generate high frequency carrier waves. Then what did we discuss? We saw what is eddy current and we saw its applications also that are possible. Right. In your textbook, there are 4 or 5 applications that are given. You can just go through it. Now you understand better. So that is a self-study thing. Any doubt, you just reach out to me. Apart from this, yeah, we are done with 7 and 6 chapter as well. Is there any other doubt that you have? Is it clear? So can we start discussing the papers from tomorrow? So 2nd, 3rd, and Monday we'll discuss 4th. So did I discuss capacitance? Did I discuss electrostatic potential capacitance? No. Okay, tomorrow we'll discuss that. And then we'll go for current electricity and moving charges and magnetism. Okay. So is there any chapter that you want me to help you? Problems? Won't say all 7 chapters I can't. Other chapter you need any help? You have studied, but it is very tough. Okay, think and let me know by tomorrow. What is the time? 5:50. So I don't want to start the paper also. Let's see. Do you have a second paper? No problem. You can look at my problems from there. Full of problems. Chapter problem. Is one of the, but you have, I gave you all the formula. You need to use them. Maybe we can discuss few problems before we wind up. Okay. So this is your electrostatic potential and capacitance test. Okay. So the question, are you able to see this? You guys are able to see? Which one is better? This one or this one? This is better. Huh? Okay. So there are 2 condensers. Condensers means, what are condensers?
Capacitor.
Condenser is another name for capacitor. So 2 condensers, one of capacity C and the other of capacity C/2 are connected to a V-volt battery as shown in the adjoining figure. The work done in charging both the condensers fully is. So how do you do them? So since they are in parallel, what is common between them? The potential drop is constant. So potential drop is constant means the energy across the first capacitor is how much? U1 is equal to half CV square and U2 will be half C/2 into V square. So this will be CV square by 4 and this will be half CV square. So what is going to be the total value? This is how it works. 3/4 CV square. Okay. So those were online. Any doubt?
Sir, we can also do like finding the effective capacitance and then
Find equivalent capacitance and then do. That is also right. It's the same thing. I've already solved this paper. There is a copper plate of thickness D. which is placed inside the parallel plate capacitor of plate distance D and area A, as shown in the figure. The capacitance of the capacitor is C dash is equal to epsilon naught A divided by D minus T plus. So what is the word they use? They use the word copper. Copper is conductor. So since it's a conductor, its dielectric constant is infinite. If you take it and substitute it here, you will get epsilon naught A divided by D minus D. Option C is the right answer. Right? So in which of the states shown in the figure is the potential energy of the electric dipole maximum? So what is the formula for potential energy of a dipole? U is equal to minus PE cos theta. So U has to be positive with the maximum value. When will it become positive with the maximum value? When theta is equal. So theta is equal to 180 degrees. Means the angle between the electric dipole and dipole moment and the electric field should be 180 degrees. Which one satisfies? This is the direction of dipole moment. This is the direction of electric field. So option C is the right answer. Understand? So there is an electric charge 10 power minus 3 microcoulomb, which is 1 nanocoulomb there, which is placed at the origin of XY coordinate systems. XY coordinate system. There are 2 points A and B which are situated at root 2, root 2 and 2, 0 respectively. The potential difference between the points A and B would be. Why? Why is it 0? It's not 0, no? Then what is it? So where is the charge placed? The 0 only. Where is the charge placed? At the origin. Where is one of the points? 2, 0. Where is the other point? Root 2, root 2. What is the distance between both? So here the distance is 2. Here also the distance is 2. The same charge at the same distance will generate the same potential because it will be a part of the equipotential surface. So potential difference between any 2 points on an equipotential surface is 0. Purida. Same distance from the other. That's right. So capacity of a parallel plate capacitor is 10 microfarad when the distance between the plates is 8 centimeter. So C is equal to 10 microfarad when the distance of separation between them is 8 centimeter. If the distance between the plates is reduced to 4 centimeter, then its capacitance will be. So C dash, so C divided by C dash will be what? Or C dash divided by C will be equal to epsilon naught A divided by D dash divided by epsilon naught A divided by D. These two will get cancelled. D divided by D dash, which implies C dash is equal to C into D divided by D dash. C is how much? 10 into D is how much? 8. D dash is that what you told? 20 only, no? 20 microfarad. It gets doubled. So read the statement carefully. electric potential and electric potential energy are different quantities. Is that right? Yes, they are. For a system of positive discharge and point charge, electric potential energy is equal to electric potential. Read the point carefully. For a system of positive discharge, you have a positive discharge. They didn't say unit positive discharge. They told it's a positive discharge. And you have a point charge as well. The point charge might be positive or negative. Electric potential energy is equal to electric potential for that kind of a system. Is it right? No, it is not. Because when you define electric potential, what will happen? The sign of the charge is taken into consideration. That is one of the things. And when you don't know the magnitudes and the distances you're trying to speak about, you cannot say anything about the potential or potential energy. So here they try to say that the first one is right, but R is false. Okay, one last problem. If the distance between the parallel plates of a capacitor is half, it is reduced to half, and dielectric constant is made 3 times, then the capacitance becomes 6 times. Is that right? Yes, it is. Capacitance of the capacitor does not depend upon the nature of the material of the plates of the capacitor. It does not depend. Then what does it depend on? Some material means you can use insulator also in the place of conductor. Is that what you're trying to say? So it is actually slightly ambiguous, no? Capacitance of the capacitor does not depend upon the nature of the material. So nature in the sense I can say whether it is a conductor or an insulator also. If you see the basic definition of conductor, what is capacitor? What does it state? If you have 2 conductors which is separated by a dielectric medium, then you call it as a capacitor. So according to me, this is false. But they've given it as true, but it is false. Because when capacitance of the capacitor does not depend upon the nature of the material, then I can say I can use a insulator also. No, I will not use. Because it is not easy for us to charge with an insulator. So first of all, you are saying, why do we use a dielectric in a capacitor? What is the logic behind the design? To store the charge. Correct. But for you to give the charge, which material can take the charge in the first place? Conductor. That is why the outside needs to be a conductor. But inside you have a dielectric only for the charge which is received to be stored. So 2 conductors separated by dielectric medium. Slightly ambiguous actually. This is the problem with assertion. You have multiple options. But according to my understanding, what I'm trying to say is, does it make sense in the first place? Right. I'm saying when they say nature of the material, it can be a dielectric also. Right. So I cannot conclude saying that doesn't work. So it's false only. Right. So the remaining problems will continue tomorrow. Yeah. So I'll see what. Download பண்ணியாச்சு. அதை கனெக்ட் பண்ணி guys will wind up, okay? those who are online.
Okay, sir. Thank you.
Thank you, sir.
Yeah.